I'm just taking the first case where my probability is correct. The probability of getting the actual transmitted one is correct. It means that I am transmitting M1. So at the receiver also, I am able to estimate M cap, which is nothing but M1. Okay, so this is what the correct decision. Okay, so average probability of the correct decision is given by PC, which is denoted as average probability of correct decision. Correct decision in the sense whatever, as I've already mentioned, based on this x1, x2, xn values, the vector decoder, it has to estimate which was transmitted. Okay, so here I'm taking the correct probability. Okay, correct probability is given by PC. Okay, correct decision probability is given by PC, which is equal to probability of mi sent. Mi sent, since mi is sent, mi is only received. Okay, mi sent provided x is already received. That is what the conditional probability. Okay, based on this x received, we are able to decode mi. Okay, that is what this conditional probability says. Okay, this is the average probability of correct decision. Okay, so now this is the correct decision. You know that the total probability, the correct decision plus the error will be equal to 1. Okay, so here I will also determine what is my error probability. Error probability will be equal to P is equal to 1 minus PC. Okay, so 1 minus PC, I have taken the error probability. Okay, probability of symbol error or error probability. Okay, so error probability I have denoted as PE. So PE is equal to 1 minus PC. Okay, what is PC? PE is equal to 1 minus PC is nothing but I have already given you probability of MI sent X received. Okay, so this is the probability. This error probability is when M cap is not equal to Mi. Okay, so generally I have the correct probability and the error probability. So which should be maximum and which should be minimum? Which should be maximum and which should be minimum? See, I am repeating the same question which I've asked on that day also. Are you able to hear me? Are you able to hear me?
Yes, ma'am.
Yes,
Okay,
ma'am.
then answer me. Is my question clear to you? See, I have determined two probabilities. I'll write again. I have determined two probabilities. One is decision rule. See, here I have to provide the decision rule to the vector decoder. What it has to do based on your vector x, where vector x is nothing but x1, x2, so on, xn, your vector decoder at the receiver has to determine whether which is transmitted. M cap value it has to estimate. Okay, for this I need to give the decision rule. Okay, in order to, before going to the decision rule, I am determining two probabilities. One is the correct probability, which is given by probability of, generally conditional probability we'll use because mi is transmitted, mi is transmitted and x will be received. Okay, so since mi is transmitted, for the correct probability mi should be received also. Okay, so whatever is transmitted, this indicates whatever is transmitted it is received also. Okay, so mi sent, x received, received. Okay, so this is the conditional probability. So this is nothing but the correct probability as well. So I'm taking PC is equal to probability of mi sent, x received. Okay, so this is the correct probability, correct decision. Okay, correct decision in the sense, okay, fine, you have transmitted one, so I have received one. Okay, that is what this correct probability indicates. Okay, we'll define one more probability, which is nothing but the error probability, symbol error probability, okay, which is given by, you know that the total probability will be equal to 1 always. Okay, so your PE will be equal to 1 minus PC. So P will be equal to 1 minus PC, which can be represented as 1 minus probability of mi sent, x received. X received. This is a error probability. Okay, now my question is, which should be maximum and which should be minimum? Correct probability should be maximum or the error probability should be maximum? Why nobody is answering? Prajwal?
Ma'am?
ಅರ್ಥ ಆಗ್ತಿದೆಯಾ ಆಗ್ತಿಲ್ವಾ?
ಅರ್ಥ ಆಗ್ತಿದೆ ಮ್ಯಾಮ್.
Then you answer me, no, which should be maximum anta keltidini. There is the error probability and the correct probability. Which one should be more? Correct probability should be. Correct probability means, what do you mean by correct probability? Correct probability in the sense, see, if I am sending one, if you are able to receive one, okay, that probability of getting one at your end when I am transmitting one is said to be the correct probability. See, let me consider I am transmitting one to you. Okay, so you are calculating the probability of getting one. Okay, that is what the correct probability that you are determining. Okay, I am transmitting one, but you are receiving 0. Okay, so there is error in the received bit. Okay, so it means that the probability, if you try to calculate the probability for error, okay, if that you will have some probability of error. So my question is, probability of correct thing should be more or probability of error should be more, so that my transmission will be correct? Okay, fine, I will only tell you. So correct probability should be always maximum. Okay, maximum. If the correct probability is maximum, then only you'll be able to receive this transmitted bit. If I'm transmitting 1, you'll receive 1 only. If I'm transmitting 0, you'll receive 0 only. Okay, so if the correct probability is more, then only you'll be able to receive the signal properly. In the same way, PE is nothing but the error probability. Error probability should be less always. Error should be less. Okay, so in order to make your error less, you need to have PE less. In the sense, I have to minimize PE. Okay, I have to minimize PE. Okay, in order to minimize PE, I need to have the I need to compute the probability in such a way that if MK is sent, okay, instead of I'm just taking it as K. If MK is sent, X is received, this should be maximum. This should be maximum. This should be maximum. Only it is nothing but your PC should be maximum. Okay, I can iterate this decision rule in two ways. Either I can say that PC I have to make it maximum, or I have to make PE minimum. Okay, in order to make PC maximum, the correct probability of MK sent X received should be maximum. Okay, so this should be maximum when K is equal to I. Okay, or from this decision, I can give the decision rule as see, you'll be calculating K is equal to 1, 2, so on until M, right? So until M, you'll be calculating the correct probability. Okay, so if the probability of MI sent X received should be always greater than or equal to probability of MK sent X received. It means that, so for different values of K, you'll be calculating the correct probability. Okay, so for different values you're calculating. In the sense, I'll be calculating for when K is equal to 1. I'll be calculating when K is equal to 2. I'll be calculating for K is equal to 3. I'll be calculating for K is equal to M. Okay, so whenever you're estimating or you're finding the probability, only when your K is equal to I, you'll have the maximum correct probability. Okay, that is what it indicates. I'll just reiterate again. See, PC should be maximum. Okay, so if PC should be maximum, PE should be minimized. Okay, or I can say that to make PE maximum, I need to use a conditional probability where this one, probability of MK sent X received, should be can be this should be made maximum. Okay, so from this statement here, I'm calculating for different values of k is equal to 1, 2, 3, so on until m. Okay, I'll be calculating the conditional probability for different values of k. Okay, in order to state the decision rule, what I'm writing the decision rule as probability of mi sent x received for all of which should be greater than or equal to probability of mk sent x received. It means that let me consider when k is equal to 1, I've calculated the probability. Okay, and for k is equal to 2 also I've calculated the probability. So let me consider when k is equal to 1, I've got the probability of 0.8. Okay, when I have calculated when k is equal to 0, I've got it as 0.2. Let me consider I've got it in this way. Okay, so I need to take decision in favor of this. Okay, so that is what this probability of mi sent x received is greater than or equal to probability of mk sent x received. Okay, so if you observe, the probability in this case is 0.8. The probability in this case is 0.8. So whichever is greater, that I need to take as my bit transmitted. Okay, so this is the decision rule which I have. So in order to design the receiver, see, still I have not gone with the receiver designing. Okay, so if I want to design the receiver, I need to consider this rule. Okay, this rule, whatever I have stated here, I need to consider this rule. Okay, only when this rule is satisfied, I'll be able to design the optimum receiver. This decision rule is also said to be optimum decision rule. How we are calculating the probability here, you don't worry right now. Okay, in the third module, we'll study how to find the conditional probability. Okay, for different schemes, how to find the conditional probability, we'll see there. Okay, here I'm just giving you the decision rule. Okay, so this is said to be the optimum decision rule. Okay, so based on this optimum decision rule, we'll be designing the optimum receiver. Is this clear? Is this clear? Have you understood what I've stated here? Dipshi?
Yes, ma'am.
Then why are you not responding? Prajwal? Nisha? Nisarga?
Yes, ma'am.
Is this clear, ma?
Yes, ma'am.
Okay, fine. So here, this is what the decision rule. Okay, so based on this decision rule, we will decide which bit is transmitted, whether M1 is transmitted or M2 is transmitted or MM is transmitted. That is how we will find. Okay, now we'll go to the, instead of using the probability, we can also use the log likelihood function. Okay, I have already introduced log likelihood function, which is nothing but here conditional probability density function. Okay, so the conditional probability density function is said to be the log likelihood function, because this will it will tell you how likely it is that that certain data point has occurred. It means that, see, let me consider mi is nothing but m1. Okay, so using this conditional probability density function, we will be able to identify how much how much likely in the sense how much exactly this is this data point will appear at the receiver. Okay, that will be given by the likelihood function, which is said to be likelihood function, which is given by fx of x. Here I'm taking the conditional probability given mi. Okay, so this is the likelihood function, or it is also said to be the conditional likelihood function. Okay. Okay, so before going to in detail about this likelihood function, all that, I'll just go to the next topic of the same. Next topic in the sense, see, whatever I have given until now, it is all introduction only. Introduction. Okay, now I'm going to the actual syllabus. Okay, which is nothing but the maximum likelihood receiver. Okay, maximum likelihood receiver in the sense, that's what, as I've already mentioned, you'll receive X. Okay, from the X you need to design a decision rule. Okay, I'll get X. Okay, from this X I have to design a decision rule where based on this decision it will tell us which bit is transmitted. So it will let you estimate M cap. Okay, so for that we will be considering the likelihood function. Okay, using the likelihood function we'll be designing the likelihood receiver. Okay, so again I'll just tell you what all you need to write here. So first the correct probability which is given by probability of Mi sent what is it, X received. Okay, you need to start from here again, and error probability is given by 1 minus PC, which is nothing but 1 minus P Mi sent X received. All this you need to write. Okay, so even in the notes which I have given, I have written this again. Okay, then the optimum decision rule, which is given by probability of Mi sent X received greater than or equal to probability of Mk sent X received. Okay, so for all K is equal to 1, 2, so on M, and K not equal to I. Okay, K not equal to I. So always for all the values from K is equal to 1 to M, I need to find the probability, and whichever probability is more, based on that we'll be able to identify which receiver is which symbol is transmitted at the transmitter end. Okay, so as I've already mentioned, we can also take the we should take the likelihood function. Okay, so using the likelihood function we'll be able to design the receiver. Okay, if you just recall, the likelihood function I have taken as fx of X given Mi. Okay, so this is the vector, and this is the observation vector, and this is a sample. I think you people know how to which is your X and which is your X. Okay, that is what I'm using here. So conditional probability density function for a vector X is nothing but whatever you have received. Where is that? X is nothing but whatever you have received, this vector. Okay, so X is the observation vector, and this x1, x2, xn, all these are nothing but the sample values. Okay, again each x1 will have different values. It will again be the set of real numbers. It may be either 0.9 or it may be observe. I have represented fx of x is equal to, and since they are statistically independent, I can write the conditional probability function as pi j is equal to 1 to n f xj of xj given Mi. Okay, so if you just recall, this is what I have already represented, and I have told you I'll be using this in my further discussions. Okay, where I is equal to 1 to so on M. Okay, these all equations I've already shown you. Okay, since they are independent, statistically independent, I'm just taking the multiplication of each sample value in the sense x1, x2, so on xn. Okay, so this I've shown you before writing this equation. I have represented that, if you just recall. Okay, so here fx of and if you just recall xj is nothing but sij plus wj. Okay, sij is some constant value, wj is a random variable. Okay, and this is a Gaussian random variable. Since wj is a Gaussian random variable, even xj will be Gaussian random variable. Okay, so for that we have calculated what will be the conditional probability density function of each observation vector xj. Okay, it is given as f xj of xj by mi, it is given as 1 by root pi n naught. I have already explained you how I've got this. I've got from the Gaussian probability density function. Okay, so Gaussian probability density function, in that I have substituted mu value and sigma value, sigma square value, variance value, mean value and the variance value, so that I've got f xj of xj by mi as 1 by root pi n naught exponential of minus 1 by n naught into xj minus sij whole square. Okay, so this is what the equation I've got for each vector x1, x2, so on like that. Okay, and if you try to substitute this in this equation, this will name as a, this will name as b. If you substitute a in b, f x of x given mi, all these equations have already represented. So you'll get pi n naught whole power minus n by 2. Okay, when you substitute x1, x2, x3 individually here in this equation, then it will turn to, because this I have already written, exponential of minus 1 by n naught, it will turn to summation j is equal to 1 to n. This I have already shown you, xj minus sij whole square. Okay, so this is the probability density function which you have. Okay, and if you just recall, I need to maximize the decision rule. Okay, so decision rule, which is your decision rule? This is my decision rule. Okay, so if you just recall, if you just check this, I need to make the probability function maximum. Okay, so in order to make the probability function maximum, what I'll do, I'll take the log function for this. Okay, why I'm taking the log? In the sense, logarithm function is the exponentially increasing function. Okay, so because of that, since I want to make this likelihood function maximum. Okay, so based on the based on making this likelihood function maximum, I'll be able to determine which bit is transmitted. Okay, so in order to make this likelihood function maximum, I'll be taking a logarithm function on both the sides. Okay, so logarithm function is nothing but the metric or the measure which we will be able to take the decision in favor of the transmitted signal. Okay, so for that reason, what I'll do, I'll take ln on both the sides, this side also, this side also. So it will become as, from here whatever I'm doing, it is new for you. Okay, I'm taking, see this one how I've got, I've already explained you. Now after this step, whatever I'm doing, you should concentrate, because based on this rule only we'll be designing the maximum likelihood receiver. Okay, so here what we are doing, see, as I've already mentioned, you need to maximize this function. This conditional probability function should be maximum. Okay, so in order to maximize this, I have to further analyze, so that for what values of xj you'll be able to get the maximum probability, so that you'll be able to take the decision in favor of the transmitted bit. Okay, so for that reason, I have to further analyze. So in order to further analyze, what I'm doing, I'm taking the logarithm. Why I'm taking the logarithm? Because logarithm function is the exponentially increasing function. Okay, so since it is the increasing function, I'm taking the logarithm function. And see, whatever I apply, it should not change the meaning. So that is the reason what I'll do, I'll take log on both the sides of this equation. This I'll name as equation C. Apply ln on both the sides. Ln on both the sides. Okay, so ln of fx of x given mi is equal to ln of pi n naught whole power minus n by 2 exponential minus 1 by n naught summation j is equal to 1 to n xj minus sij whole square. Okay, I have just taken ln function on both the sides. Okay, so since I have to maximize this conditional probability density function, after I have applied ln on both the sides. Okay, so now further simplification. Ln of AB can be represented as ln of AB can be represented as log AB can be represented as log AB can be represented as, are you people able to hear me? Sumant Gowda. Are you people able to hear me?
Yes, ma'am.
Then you answer me also, no? Everybody, not only Prajwal, everybody in the class.
Yes, ma'am.
Kavya, are you there?
Yes, ma'am. Yes,
Kavya,
ma'am.
log AB can be represented as
Log A plus log B.
Matte, like why you not telling me? Okay, so ln of AB can also be represented as ln of A plus ln of B. Okay, so I'll take this term separately and this term separately. So this time I'll consider as A and this term I'll consider as B. So it will be ln of pi n naught whole power minus n by 2 plus ln of exponential power minus minus 1 by n naught summation j is equal to 1 to n xj minus sij whole square. Okay, so this is equal to ln of a power b can be represented as b ln of a. Okay, so I'll use the same thing. I'll use the same thing here. So it is minus n by 2 ln of pi n naught plus it is nothing but ln, again it is exponential e power something you have, right? So e power a can be represented as a ln of e. So I'll write in the same way. So it is nothing but minus 1 by n naught in place of exponential e power a I have, in place of a you have this function. So I'm just writing it minus 1 by n naught summation j is equal to 1 to n xj minus sij whole square into ln of exponential is nothing but e. Okay, what is ln of e? What is ln of e? What is ln of e? Ln of e value is how much? What is the base for ln? You people don't want to answer, or what? I'm not understanding. Kavya? Kavya,
Yes, ma'am.
what is the value of ln of e? You know it or not? Any other person in the class? Aditya? Aditya?
Ma'am,
Tell me the value of ln of e.
1, ma'am.
Then yeah, I need to call in each and every person's name and ask. Its value is 1, right? ln in the sense log base e. Log base e. Log base e value is 1. Okay, so ln of e value is 1. So this is what I've got. Okay, so what is more like what is my condition here? I have to maximize the likelihood function. Right, if I want to maximize the likelihood function, see if you observe this, anyway, this is a constant value, right? So this is a constant value because minus n by 2 ln of pi n naught. N is some constant value, pi value is 3.14, n naught is nothing but ktb. Okay, k is the Boltzmann constant and tb is the temperature. So everything is constant here. So this term is constant. Okay, the first term in the equation is constant. Okay, this term is constant. So on what it is depending, I need to maximize this function. Okay, so only when I maximize this function, I'll be able to get the correct probability. Okay, so since I have to maximize this function, anyway, this is a constant. So on what it is depending, here I have the variable xj is variable, right? Because x vector I'm getting as x1, x2, so on xn. Okay, and again this x1 can take any value of real numbers. Okay, so small x1, small x2, so on, small xn are nothing but the sample values of this x1 vector. Okay, so this can change x1, x2, xn, it can be any value, right? So based on this value, my condition will change. Okay, so if I want to maximize this log likelihood function, anyway, since the first term is constant, I will not be able to do anything with the first term. So what I need to change so that my log likelihood function, this is said to be log likelihood function. Okay, how this log likelihood function can be maximized. Okay, only when you maximize it, you'll be able to get the correct decision. Okay, correct decision will be correct decision in the sense correct decision. If you take the correct decision, then it means that whatever is transmitted, you'll be able to receive, right? So in order to do that, I'm maximizing this log likelihood function. Okay, so in order to maximize this log likelihood function, the first term is a constant. So I have to do something with this so that this function will be maximized. Okay, so now what I need to do, anyway, 1 by n naught is a constant, so I can just take this function. Okay, this function, which is nothing but summation j is equal to 1 to n xj minus sij whole square. Okay, only this function I have taken. So how should be this function? It should be maximum or minimum. This function should be maximum or minimum. I need to maximize this. Okay, so I have minus 1 by n naught summation j is equal to 1 xj minus sij whole square. Okay, my question is whether this term should be more or less so that my log likelihood function will be maximum. Prajwal, can you answer me for this? Prajwal? See, I want to make this function maximum. Andre more value. I have to get more value for this log likelihood function. So this is a constant. So I cannot change anything with this. Okay, so the only option is I can change this one. Anyway, 1 by n naught is a constant. So only option is I have to increase this value xj minus sij whole square value, or I need to decrease this value so that this will become maximum. So my question is whether this term, the same term I have represented here again. So whether this term should be increased or decreased. That's what my question. If I increase this, what happens? If I'm increasing this, what happens? The negative value will be increasing, right? Yes or no?
Yes, ma'am.
If negative value is increasing, what happens to the overall value? Anybody can answer me. See, I am increasing this value, ma. Okay, if I'm increasing this value, what happens? This is minus term, minus of this value. This value will increase. Okay, if this value is increasing, see, I have some constant value 10. Okay, minus, I'm increasing it from 2. Okay, so 2, 3 like that I'm increasing. Okay, so what happens to the overall value? X is equal to 10 minus this y, and where this y is increasing from 2, 3, 4 something like that. Okay, so what happens to overall value x? That is what my question. What happens to the overall value if I'm increasing that value? See, y is equal to some 10 constant minus x I have, where x I'm increasing from 1, 2, 3 so on like that. So if I'm increasing x value from 1 to some value, what will happen to y? Y will increase or decrease? That's what my question. It will decrease, right? So if it is decreasing, my condition of maximizing this log likelihood function will not satisfy. Okay, now let me take y is equal to 10 minus x only. Now what I'm doing, I'm reducing x from maybe 5, 4, 3, 2, 1 like that. I'm minimizing it. So what happens to overall value of y?
Increases.
It increases, right? So what is the condition I need to take here? In order to have maximum likelihood function value, I need to minimize this. Okay. See here, what I'm doing is I'm deriving the condition. Okay, condition based on your maximum likelihood function, so that based on that I'll be able to determine whether the signal is what is that the decision is made proper or not. Okay, so that is what we are finding here. So this should be minimum. Okay, only when this is minimum, only when this is minimum, I'll have the correct decision. Okay, so minimum, if you observe, it is nothing but xj minus sij. Okay, sij is the transmitted signal. Sij is the transmitted signal, vector. If you just recall, mi first we are converting to si. Where is that? mi you are converting it to si. Mi you are converting to si. Si is nothing but si1, si2, sin. Okay, so it is nothing but vector si. Okay, so here if you observe, if I try to represent this function geometrically, graphically, so my see, I have xj vector. Okay, this is my xj vector, and I have sk vector. Okay, or sj vector only. I'll take as sj vector only. One second. I'm representing it graphically. Okay, so what will be the axis when I'll represent it graphically? What will be this axis? Orthonormal basis function, right? Phi 1, phi 2, so on, all these are perpendicular and they form the orthogonal coordinates of the vector space. Okay, signal space or vector space. Okay, so here this xi minus sij indicates if this is vector xj and this is vector sj. Okay, so this difference, okay, if this difference is minimized, okay, if this difference is minimized, what will happen? If this distance is minimized, then xj and sj will match with each other. Okay, if xj and sj are matching with each other, then I can say that the decision is made in favor of correct bit that is transmitted. Correct bit that is transmitted. Okay, so how practically you are applying that we'll see in the next module, ma. Here we are just learning theory related to this particular concept. Okay, so here xj minus sij whole square. Okay, so the length square, this is nothing but the length square. Okay, length between x and s. Okay, si. Okay, x vector and si vector. If you are taking the length of that and squaring it, okay, you know that this is the length if you just recall, I have just represented it in this way. Okay, so this double perpendicular lines here, double parallel lines here will indicate that it is nothing but the length of the vector. Length of the vector. Okay, so if the distance between this vector xj and sj, this is a transmitted vector and this is a received vector. Okay, if the distance between these two, or square of the distance between these two are reduced, okay, then I can say that the error is less. Okay, that is what it indicates. Okay, so now let me take back this condition and let me analyze further. Okay, to design the maximum likelihood receiver. So let me take the equation. Summation j is equal to 1 to n xj minus skj. Skj only, no? Sij. Okay, so here we are taking k is equal to I. Okay, only when k is equal to I, it will be transmitted bit will be the received bit. Okay, so I'll write as xj minus skj whole square, which can also be represented as j is equal to 1 to n xj minus sij whole square. Okay, so this I'll just try to expand. Okay, summation j is equal to 1 to n xj minus sij whole square is equal to I'm just expanding this summation. So j is equal to 1 to n xj square minus 2 xj sij plus sij whole square. Okay, so again I'll just take summation for each term. So summation j is equal to 1 to n xj square minus 2 summation j is equal to 1 to n xj sij plus summation j is equal to 1 to n sij square. Okay, so if you just observe here, this is nothing but the energy of the received signal. X we are getting right, x is equal to x1 x2 so on, xn we are getting right. So this is nothing but this will give the energy of the signal, energy of the received signal. Okay, so this will be some constant value, and when it comes here, this is nothing but the minus 2 summation j is equal to 1 to n xj sij is nothing but this is just found by taking x transpose into si. Okay, so when you multiply x transpose, this is x, so x transpose will be x1 x2 so on xn. Okay, that if you multiply with i1 si2 so on sin, this is what I'm going to get. Okay, so this will give the inner product of observation vector x and si or sk, anything si or sk, however however it is, it's fine only, because here the condition is k is equal to I. Okay, so this is what that. Okay, then when it comes here, it is again nothing but sij whole square, in the sense si1 square plus si2 square plus so on sin square. Okay, so again this term is nothing but energy of the transmitted signal. Okay, energy of the transmitted signal or transmitted vector. SA is the transmitted vector. So this is again nothing but the energy of the transmitted vector. This is the energy of received signal. This is nothing but the inner product of received vector and transmitted vector. Okay, and this is nothing but the energy of transmitted signal. Okay, and one more thing, if you again observe, this is independent of I indicates the transmitted bits rate, so this is independent of I, whereas this and this are dependent on y, I. So what I'll do, I'll just take this equation once again. So I will write as what is that? Summation j is equal to 1 to n xj minus sij whole square. See, it can be I or k. Anything is fine. It is I or k. Both are same only. Okay. Sij is equal to summation j is equal to 1 to n xj square. So this is not depending on I, and whereas here it is depending on I. So what I'll do, I'll take two common. So summation j is equal to 1 to n xj sij minus 1 by 2. This is nothing but energy of the transmitted signal. So EI or EK, anything is fine. Okay, so this is a like equation that I've got when I've considered only summation j is equal to 1 to n xj minus sij square. Okay, so again, if you observe, this is independent of I. Okay, so since this is independent of I, I'll not consider this, and anyway, this is nothing but the energy of the received signal. It will be constant. Okay, and here this is depending on I, and even this is depending on I. Okay, so I'll now what I'll do, again I'll take only this portion. Okay, and again you here again I want you people to tell me to minimize this. See, I've already mentioned we need to minimize this function. Okay, this function should be minimized. Okay, in order to minimize this is a constant. Okay, so what should be, how should be this value? This value should increase or decrease? That is what my question. So I'll take only that portion. Okay, summation j is equal to 1 to n xj sij or skj sij minus half ei. Okay, so now my question is, from this, whether this portion should be maximized or minimized. To minimize this should be maximized or minimized. This is constant because it is just giving the energy of the received signal. Okay, so now from this I need to confirm whether this value should be more or less. Okay, so since I have to minimize, it means that this should be increased. If this is increasing, then this will decrease. Okay, so that is the reason I will take the final, after this I need not further analyze. I will take the final maximum likelihood function as yk, which is equal to summation j is equal to 1 xi into sij minus half ei. This should be maximum. Only when this is maximum, I'll be able to take the decision of the vector in the correct region. Z is nothing but the region, so I'll be able to, no, I'll not introduce that term now. Okay, let me just say that this should be maximum. Only when this is maximum, I'll be able to take the decision in the correct region. Okay, correct region in the sense, that's what I'll be able to decide whether M1 is transmitted or M2 is transmitted or M3 is transmitted. Okay, so this is the maximum log likelihood function that is to be designed at the receiver end, so that the decision will be made in favor of the correct variable. I hope you people are understanding. I don't know. Anyway, I'll just pass you the notes also. You go through it. Okay, and that's what. Anybody has got any doubts, you can ask me. I'll just refresh everything. So here I need to find the log, like I will just explain once again. So here I need to design the receiver in such a way that it will reduce the probability of error probability it will reduce. Okay, so the decision rule is this one. So always the probability which you are finding should be maximum than the other bits probability. Okay, so only in that case you'll be able to identify if the probability of correct decision is maximum, then only you'll be able to identify the correct symbol that is transmitted. Okay, so for that what I have done, I have considered the log likelihood function. This is said to be the likelihood function. Only when I apply log, then it will become log likelihood function. Okay, so this is a function I have considered. Okay, so from this function, this is the overall conditional probability density function, which is also said to be the likelihood function. So here what I need to do, I need to maximize this function. Only when I am able to maximize this function, I'll be able to take the decision towards the correct transmitted bit. Okay, so that is the reason I need to maximize this. Okay, so since I want to maximize this, I'll try to do some mathematical analysis and develop an equation which will tell me on what the decision should be done. Okay, so for that you already know, since the vector x is statistically independent, you'll be able to find the overall conditional probability density function by taking the probability density function of individual vectors. Okay, so that is nothing but multiplication of all individual vectors. And you know that xj, whatever vector you are getting at the output, those are nothing but the Gaussian random process. Okay, since it is a Gaussian random process, you know that for the Gaussian random process, you will be able to denote the equation by taking 1 by root 2 pi sigma square exponential minus x minus mu whole square, not minus of, minus x minus mu whole square divided by 2 sigma square. Okay, so this is what the equation you have. Okay, so you already know what is mu for xj and what is sigma for xj. Substituting them, you have got this equation. Okay, again, this is for each vector x1, x2, like that. Each vector xj indicates each vector. So since you have xj for each vector, I need to multiply x1, probability density function of x1, probability density function of x2, probability density function of xn, like that. So when you multiply them, this is what the equation you're going to get. Okay, now what is my condition here? I need to maximize this likelihood function. So here what I'll do, I'll apply log on both the sides to get the correct decision rule. Okay, so I'm applying logarithm because logarithm function is the exponentially increasing function. Okay, so monotonically it is increasing function. That is the reason I'm taking it as ln on both the sides. Okay, then I have applied the loss of log function. Then I've got this equation. Okay, and if you observe in this equation, the first term is a constant. And whereas the second term, it is not constant because there you are taking the difference and xj, sij difference, everything is taken. It is not the constant, but whereas this term is constant. So I need to maximize this. Since I want to maximize this, I need to take the only way to maximize the log likelihood function is I need to minimize this. Okay, so in order to minimize that, I've taken that expression. Okay, I've taken that expression. Okay, and then I've expanded. Okay, after expansion, I've got three terms. Like this. Okay, so I've got three terms like this. Okay, where the first term indicates the energy of the received signal and second term indicates the inner product of xj and si. Okay, here we are taking the inner product between the x received vector and the transmitted vector x and sk or si. Okay, transmitted vector. So here we are taking the inner product between these two. Okay, and when it comes to the last term, this is nothing but the energy of the transmitted signal. Okay, since it is the energy of the transmitted signal, even this is a constant. I have just indicated with energy ei. Okay, and this is what the term. Okay, now what I did, I have just taken -2 common so that my next equation has reduced to this one, reduced to this part. Okay, so again the condition here is I need to minimize this difference function. Okay, I need to minimize this difference function. So in order to minimize this is anyway constant. Okay, so in order to minimize this, I need to maximize this. Only when this second term, this portion is maximized, I'll be able to minimize the overall function. Okay, so that is the reason I've taken only that portion. Second term, this is just the second term I have taken. Okay, and I'm just assigning it to yk. This is randomly I have just assigned. the name given here is yk. Okay, so this is a final equation of maximum likelihood function. Okay, so by maximizing this function, okay, I'll be able to take correct decision in favor of m1, m2, so on, mm. Okay, so this is all related to the maximum likelihood receiver. Hope this is clear to all of you. I'll just pass on the notes. You people can just go through the notes as well. Okay. Anybody has got any doubts? See, like all these concepts will be more clear only when you're very thorough with random process. Otherwise, also like I'm explaining why we are going with that function at that particular moment. All that analysis also I'm giving you. Okay. Hope this is clear to all of you. Are you all understanding? Huh? See, if you keep quiet, no, I'll not understand anything, ma. That's all for the day. I have done with my class. If anybody has got any doubts, you please ask me. Otherwise, you can leave the meet. Prajwal? Prajwal?
Ma'am.
ಅರ್ಥ ಆಗಿದೆಯಾ?
Yes, ma'am.
ಎಲ್ಲ ಅರ್ಥ ಆಗಿದೆಯಾ? Everybody else? Rupashri? Rupashri? Teja? 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 Bhavna? Bhavna? Bhavna?
Yes, ma'am.
Is this clear? Is derivation clear?
Yes, ma'am.
Same it Rutma. Bhavna?
Yes, ma'am.
Hope it is clear to you, right? Out of 100%, how much you understood? Tell me in percentage. Okay, fine. You people can leave.